Okay, good morning, everyone. So last time, let me remind you that we were talking about perturbation theory. And this is in section 10.1 of the notes. And so the idea here is that we're starting off with some Hamiltonian, which consists of a part H0, which is small, and another part W, which is complicated perhaps, or just difficult to deal with. And what we want is to solve the eigenvalue equation for that Hamiltonian. So we want to act on some eigenstate psi sub n and get back some perturbed energies E sub n. And our strategy for doing this was to try a solution of the following form: that the eigenstates are just the eigenstates of H0 plus an infinite sum that we're not going to compute all of. But in principle, it's an infinite sum of powers of lambda. Lambda is supposed to be something that's small. And then it's multiplied by some correction kets that we want to find. And we do the same sort of expansion for the energy. So again, it's an infinite sum, but we're only going to probably find the lowest few values in powers of lambda. And those corrections are called E sub n with a superscript k. Okay, so we're trying to do that. And these ones here are known, we assume. The eigenstates and eigenvalues of H0. Okay, so then we plugged that into this equation, and we derived, which I'm not going to rewrite, but we derived equations for each power of lambda to the k separately. So that's the basis of the strategy, is divide and conquer. We divide this very complicated equation into a set of smaller equations, one for each power of lambda. And then what we found was that the nth energy eigenstate, the first order correction, was equal to the expectation value of the perturbation. Okay, and that's probably the most important equation in the whole business, the one that we'll use the most when we have applications, for example, to the hydrogen atom. We'll want to use that equation quite a bit. And along with that, there's the first order correction to the state, which we found, although I didn't quite write it this way last time, but it's equivalent to this: a sum over all other unperturbed states M, and the coefficient of each state is the matrix element of the perturbation between the original state N and the state M that's appearing in the sum, divided by the energy difference. That is the unperturbed energy difference. Okay, so that's also an important formula, though we won't quite use that as much as the energy correction. But together, these form the first order corrections to the state and the energy. Okay, so notice in the sum that there's going to be a problem if curly E sub n, actually this should be minus m.
Yeah.
Curly E sub n minus curly E sub m is 0, but that's taken care of hopefully by the fact that we're not summing over m equals n. And that went back to the fact that if you take the inner product of n with psi nk, that's always 0. That was a choice that we made by normalization. Okay, and so that assured that we wouldn't have a problem with the denominator blowing up, assuming there are no degeneracies. Okay, and furthermore, if we look at lambda to the k, that was just for k equals 1, so lambda to the first power, but then if you looked at a general k, we found that the nth order correction to the energy looked like this. Okay, again, it's a matrix element of the perturbation Hamiltonian involving the state n and the state psi n k minus 1. Okay, so if the w wasn't there in between, that would just vanish. But the fact that the w is off diagonal means that in this basis means that this will be non-zero. And so if you know the correction to the state at order k minus 1, then you know the correction to the energy at order k. And so in some sense, all of this boils down to just finding the corrections to the state, and then the corrections to the energy you just get from this formula. So notice, by the way, if we plug in k equals 1, if we plug in k equals 1, then this right here, this right here is just psi n sub 0, or superscript 0, which is n. And so we're really just getting back this equation. So this is a generalization of what we had found above. Okay, so let's go ahead and apply that now to k equals 2 to see what happens. Okay, and we can do that because right here we have psi n1, that's going to go there. Okay, and so we get the second order correction to the energy is equal to n w, and then we have to put in here sum over m not equal to n, m matrix element m w n divided by the energy difference. Okay, and then it's just nicer to rewrite that in a slightly more compact way, because we can take the sum to the outside, and then what's in the numerator is just the complex square of the matrix element divided by the unperturbed energy difference. Okay, so now we have the energy correction at second order in the perturbation. That's at order lambda squared. And so let's go on and find the states at level k, or find the equation that would give them to us. So next, find states at level lambda to the k. And so first of all, what does that mean? That means we're going to try to write our state psi nk as a linear combination of some basis elements, and the basis elements we're going to pick are going to be the unperturbed states. Okay, so we're going to be summing over all m. And the coefficients will look like this, and that's by completeness. So really all I've done is I've rewritten the operator 1 using completeness in a fancy way. But now I can do something nice, and that is I can eliminate n from the sum. And the reason I can do that, it goes back to this right here, which last time we called the red asterisk equation, right? That tells us we don't have to include n in the sum here because it won't appear in this equation. That's why we cannot write, we can eliminate the term where m equals n. Okay, so now let's take the inner product of that equation with the ket m okay, actually, we're taking the inner product not of that equation, but of the lambda to the k equation, which I had written down last time. Okay, and so let me write out what that looks like. So there's there's going to be an m on the left, an m bra on the left for every part of this. M H0 psi n superscript k plus m w psi n superscript k minus 1. Okay, that's supposed to equal curly n m psi n k. And then there's a sum, but not an infinite sum. It's a finite sum from j equals 1 to k of the jth energy correction times the matrix element or the inner product m psi n k minus j. Okay, so we have to do something with that. The most obvious thing we can do is on the first term, we can notice that the H0 Hamiltonian acting on the bra m just gives back curly m times m. Okay, and then once we have that, this term is begging to be combined with that term because they have the same form. So who are we to deny it? Let's go ahead and combine those. Okay, and so we get curly E sub n minus curly E sub m times that inner product equals m w, I'm just moving everything else to the other side of the equation. Okay, so there's now our sum again. Okay, and so what's the point of writing it this way? So if you stare at this equation, you realize that the way I've written it, everything on the right-hand side involves only objects with order less than k for the state. So this right here and this right here are lower order. And so what that means is you can do this iteratively. If you've got the first order, you can get the second order. If you've got the second order, you can get the third order, and keep going until you're satisfied that you've done as well as you can do without going crazy. Okay, so can solve this iteratively. Okay, and so let's just do one more order beyond what we'd already done. So now we're going to do k equals 2. We already did k equals 2 for the energy, but now we're doing k equals 2 for the state, ket. Okay, and so we have m psi n2 is equal to, I'm going to divide by the prefactor, which is the energy difference. Okay, and then I'm just going to rewrite everything else with k plugged in as 2. I'm going to expand the sum and write both terms in the sum explicitly so we can see what they are. Okay, so in that very last term, what I've done is I looked at this and I said, oh, when j is equal to k, that's psi n superscript 0, which is the same thing as the unperturbed state n. Okay, so I've just rewritten it that way. And then as promised, everything else here is something we've already computed. We already computed the second order correction to the energy and the first order correction to the state. So in principle, we know everything here and we can just plug it in. Before doing that, though, remember, we only want this equation for m not equal to n, and so this term right here is just 0. So we don't have to worry about that anymore. And so everything else we can just plug in. And so this is going to look like the following. Sum over p not equal to n of m w p p w n. And then there's an energy difference n minus m. That's just coming from this overall factor. And then inside here, there's also the energy difference En minus Ep, curly En minus Ep. Okay, and then there's a term from the second term, which looks like M W N N W M divided by curly En minus curly Em squared. And that should also be an M.
Hi, Dr. Martin.
Yeah.
Can you hear me all right, first of all?
Yes, sure.
Okay, I just want to make sure my microphone was working. Oh, you just fixed some M's, didn't you?
Yeah.
And
I keep writing N when I mean M. Sorry about that.
You're all right. And then in the line above that, should that also be an En minus Em?
Yeah. Yeah. Thanks.
Yeah, I was going to mention
I
that.
figured that was a safe bet, but probably good to correct it.
Otherwise,
please no infinities.
Yeah.
Very good. So for some reason, I'm having a psychological problem with N and M today. All right. Any other issues here?
Nope, that's good. Thank you.
Okay, good. Okay, and all of this is true, of course, for N not equal to M. Okay, but going back up here, we see that that's all we need anyway. We don't need to compute this thing that we just computed when N equals M, because it just doesn't contribute to the sum. Okay, so now let's summarize what we have so far. And so really what we've done is we've done everything to order lambda squared. I think I can safely promise you that you will never have a problem in this class where you have to go to order lambda cubed. I shouldn't promise that because you never know, but I doubt it. Okay, and so the perturbed energy is equal to the unperturbed energy plus the first order correction, which looks like that. And then we found the second order correction, which looks like this. Sum overall M not equal to N. Let's see if I can keep my M and N straight this time. Okay, and then this keeps on going forever, but we've just done the first two terms. And then we have the psi sub n, which is of course at 0th order, just the state the unperturbed state. And then there's lambda sum M not equal to N, M W N over M epsilon or curly En minus curly Em. Okay, plus lambda squared. And now we have a double sum. So first of all, M not equal to N, and then P not equal to N. So when I write that, of course, I mean summing over all values except P equal to N, whatever those values be. It might be a problem where I have an infinite number of those different values. It might be a problem where I have a finite number because my state space is finite. And then sometimes, many times, even though it's an infinite sum, it turns out that only one or two terms contribute to the sum. So we'll see an example of that before the end of today. Anyway, what goes here is MWP, PWN over denominators, EN minus EM, EN minus EP, minus a sum of M not equal to N, MWN, NWM, divided by the square of the energy difference. Okay, and then in principle that goes on forever. So a couple of comments on this. One is that basically, why does this parameter lambda exist at all? It really was just there so that we could keep track of what order of perturbation theory we were working in. So one comment is it's very common, now that it's done its job of keeping track of which order it is, we can just set lambda equals to 1. So you can do this. Okay, and so why is that valid? That's just valid because you think of W as being small. So W might contain some parameter within it. Later on, it will turn out in many examples, it'll be like the fine structure constant, which is a small number, right? And so if your W is small, then you don't need lambda. You don't need to worry about lambda being small either. You can just set it equal to 1, and then you just have one less thing to write down. So that's something you can do. And another thing you can do to make this look nicer is you can just define as notation Wn prime n is the matrix element n prime Wn. Okay, and so that will just make the formulas look a little bit nicer. And also, if you stare at the formulas, you realize that's basically the only thing you ever need to compute. You need to know these matrix elements. And if you do, then you've basically solved the problem, because the only other thing that appears now is the energy differences that are appearing in the denominators. Okay, so we need these. And in fact, if you're doing anything beyond first order in energy, so first order in the state or second order in the energy, then it's not a bad strategy to just start first by computing all these matrix elements. You need to compute the matrix elements of the perturbation Hamiltonian, and then once you've got those, then it's just a matter of plugging into these awful formulas. Okay, and then the third comment here, which I've already mentioned, is need to worry if En minus any other curly E is 0 or small. Okay, for n not equal m. So obviously, if it's 0, then we have a problem, because then we're just writing down nonsense. We're writing something over 0. That doesn't make any sense. But even if it's non-zero but small, then we still have a problem, because notice that the higher order in perturbation theory, at each order in perturbation theory, we're getting an extra power of one of those denominators. And so if the denominator is just small, then our perturbation series is not going to converge. And again, everything we're doing is quite possibly nonsense. So we will have to worry about those things later. But for now, we're going to do some examples where everything works and everything's fine. Okay, maybe I should ask if there are any questions first before we start doing examples.
Professor?
Yeah, go ahead.
Maybe I should wait until after your examples. I'm just curious to know what the purpose and application of these are.
So the purpose and application is just to solve problems that you cannot solve exactly, which turns out in the real world to be almost all problems. There's a short list of things that we can do exactly, and they include, a particle in a box, harmonic oscillator, a hydrogen atom, a free particle, a few others that can be done exactly, but almost everything you run into in real life, you can't solve it exactly. It's just too complicated. And so this is how you're going to do it.
Thank you.
Okay. All right. So let's do an example. And so this example we're going to start with is a perturbed one-dimensional harmonic oscillator. You're going to get to do for homework a different perturbed one-dimensional harmonic oscillator that's slightly harder than the one I'm about to do, but not that much harder. So we start with an unperturbed Hamiltonian, which is the usual harmonic oscillator Hamiltonian, which looks like this. Okay, and that's good because we know the eigenstates and eigenvalues of that Hamiltonian, and our perturbation W is going to be minus F times the operator X. So the interpretation of this is F is a constant force. So you can think of this as we start with a harmonic oscillator and we apply a constant force to it. Okay, and we know the eigenstates N are, you can write as creation operators to the nth power divided by square root of n factorial, acting on the ground state 0. Okay, and so these exist for n equals 0, 1, 2, etc. Okay, and the corresponding energies are, we learned from studying the harmonic oscillator, h bar omega times n plus 1/2. Okay, so we always need an unperturbed problem that we can solve, and that's what it is in this case. All right, and then I had mentioned earlier that what we want to know usually first before we do anything else is what are all the matrix elements of the perturbation Hamiltonian. So we're going to need matrix elements. If you forget the constant F and the minus sign, we're just going to need matrix elements that look like this, which I think we've already computed, but let's do it again. Okay, so this is square root of h bar over 2m omega n prime a dagger plus a. Okay, now you can do this in position space, but it's usually a better idea when you can to do it, to work with creation and annihilation operators, because now you can just look at how those a and a daggers act on the state n, and they look like this. They give you back constant. Okay, oops, I made a mistake here. This should have been the state n plus 1, right? So when we act with a dagger on n, we get the state n plus 1 times a factor square root of n plus 1. And when we act on the state n, we get with a, we get n minus 1 times square root of n. Okay, and then those are mostly 0. The only time they're not 0, okay, is when n plus 1 is equal to n prime. So the first term looks like this, at delta n prime n plus 1. And the second term looks like delta n prime n minus 1. So that's good. That means when we do our sums over, infinite sums over all the states, usually only 1 or 2 terms is going to survive. Okay, and so let's in fact do this to second order. For each state labeled by n, first of all, the first order correction to the energy is equal to minus F times n x n. Okay, but according to the previous thing that we just found, that's just 0. Okay, because the previous thing we found says it's only non-zero if this, which is n prime, is equal to n plus 1, which it's not, or n minus 1, which it's not. So the first order correction to the energy just vanishes. And so when that happens, you usually want to go to second order in perturbation theory. Okay, for which our formula above tells us this. Okay, and now we see that exactly 2 terms in the sum will survive. There's a term where m is equal to n plus 1. And so that is going to equal minus f times square root of h bar over 2m omega times square root of n plus 1. And we're instructed to square that. All of that's coming from this term. Okay, and then we need to divide by the energy difference, which is curly En minus curly En plus 1. And then there's a term coming from this, which is going to be plus minus f square root of h bar over 2m omega square root of n squared, all divided by curly En minus curly En minus 1. Okay, so only 2 terms survive. This is generally known as a selection rule. Selection rules are just when matrix elements vanish, in many cases for lots of different situations. It's a selection rule. Okay, and we also need to worry about the denominators. So if we have curly En minus curly En plus 1, that's h bar omega n plus 1/2 minus h bar omega n plus 1 plus 1/2, which is minus h bar omega. And similarly, the other denominator we need is this, which is going to be positive h bar omega. And so now we can put everything together into that second order correction. Okay, when we square everything, we're going to get an f squared. Remember, f was our force that we were applying. And the denominator, there's an h bar omega. And then when we square the matrix element, we're going to get a factor of h bar over 2m omega. And then from the first term, we're going to get minus n plus 1. And from the second term, we're going to get plus n. The minus sign on the first term comes from right here. Okay, and so when we simplify that slightly, this just turns out to be minus the force squared divided by 2m omega squared. Okay, and so when we put everything together for what's the energy, it's curly E sub n plus En1 plus En2. Notice I don't have a lambda in here. I've set lambda to 1, as mentioned earlier. And so this is h bar omega times n plus 1/2 minus f squared over 2m omega squared plus things that go as higher order powers of f. So notice our correction here turned out not to depend on n, which is fairly unusual. And we'll see the reason why that happened in a little bit, but you shouldn't expect that to always happen. Usually it will depend on the state. Here it didn't depend on the state, it turns out. Okay. let's do the wave function first, and we'll only work to first order in the wave function, because the first order correction to the wave function or the state is non-zero. Okay, and so we're going to plug into our formula psi n1 is equal to sum m not equal to n m m w n curly e n minus curly e m. But again, we're going to use the fact that this is only non-zero if m differs by n from n by exactly 1 unit. And so this is minus f, that was multiplying the w. And then in the matrix element, there was a square root of h bar over 2m omega. And then there was the result of the matrix element gave a square root of n plus 1 times n plus 1 over minus h bar omega. And then there was the other term, which was square root of n times n minus 1 over positive h bar omega. Okay, and so we just need to make this a little bit prettier by getting rid of the minus signs and putting together things under square roots. Okay, and then what's multiplying that is square root of n plus 1 minus square root of n minus 1. Okay, so that's the first order correction to the state. If you want, we can write it out like this. Oops. Okay, so the state has a correction that's first order in the force, whereas the energy was second order in the force. Okay, so that's the state. And then if you want the wave function, as usual, psi n of x, you just take x inner product with psi n, and then you'd get your horrible Hermite polynomials and whatnot. All right, so remember though that when we did this, we did a non-standard normalization for our state psi sub n. And so this is not of unit norm. And so you could ask, okay, what happens if you do make it have unit norm? So to compute the norm of this state first, we need to do psi n. Okay, and so there will be a n term. And then there will be a term linear in f. But when you look at it, you realize that vanishes because I'm taking the inner product of n with n plus 1, that's 0, and n with n minus 1, that's also 0. So the term that in the inner product, or the term in the norm that's linear in f is 0. And then there's going to be a term f squared, which is what's going to happen when you take the inner product of this with itself and this with itself. And so that's non-zero. Okay, but we're not going to worry about that. We have no right to worry about that because we already dropped terms of order f squared by only writing this to linear order. And so there's no sense in worrying about these terms at all. Okay, so, but we already dropped terms in the wave function, or terms in the state of order f squared. So we don't have to bother with these either. It wouldn't make any sense. Okay, so in other words, really to the order and perturbation theory that we're working, this state really does have unit norm, even though as an exact statement, it doesn't. All right, questions on that example? So before we move on, we should mention that this example that we just did can also be done exactly. We didn't have to use perturbation theory because it wasn't that hard. So this example can be done exactly. And the way that works is by a change of variables. So we do p squared over 2m plus, let me just write out the full Hamiltonian as it was given. Okay, and then we notice that all the terms depending on x, we can rewrite like this. So I'm doing a completing the square thing. And so when I complete the square, I have to subtract off the extra part. Okay, so I've just rewritten it. And now we realize that, okay, if we just shift variables, this is the harmonic oscillator again with an extra term. This is our extra term. This is a harmonic oscillator, but instead of centered at 0, it's centered at f over m omega. Actually, that should be f over omega squared, I think. Okay. So shift variables by taking x to x plus f over m omega squared. And then the new Hamiltonian will have the same mass and omega and the same energies, therefore, except shifted. So, okay, except there's this constant minus f squared over 2m omega squared. Okay, and so in this example, we actually know the exact energies. They look like this. Okay, minus f squared over 2m omega squared. And that explains why when we did the calculation in perturbation theory, we got an answer that didn't depend on what state it was for the correction. So as a reminder, if we go back up here, we had written this down in perturbation theory, but we had plus dot, 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 because we didn't compute the third order or the fourth order or the fifth order or the sixth order. But it turns out that miraculously there's some conspiracy and those terms just cancel completely. Because here's the exact answer, and it agrees exactly with what we got just at second order in perturbation theory. Okay, so that's nice. Also, we can think about the state in the same way. We should have that the exact state, psi sub n, is equal to a translation operator by a translation by f over m omega squared, acting on the unperturbed state n. Right, and the reason we're translating by this is that's how much we shifted by. So a reminder, this right here is the translation operator, which was defined in section 4.1, in particular equation 4.1.1 was where we defined what the translation operator was. Okay, it's just something that moves you over by a displacement, oops, f over m omega squared. Okay, and if you look back at that equation, you can compute what it is. So it's the exponential of minus I times the amount by which you're translating times the momentum operator divided by h bar. And in this example, we were expanding in small f. So unlike the energy, we can't quite do this exactly, but at least we can expand this exponential and get 1 minus I f over m omega squared h bar. And then P, the operator P, if you look back what that is in terms of creation and annihilation operators, it looks like this. A dagger minus A. Okay, and that's equal to, when I simplify things a little bit by multiplying the i's together, that's 1 plus f over square root of 2 h bar m omega cubed times A dagger minus A. Okay, and that's good. That agrees. If you plug that in to here, that agrees with what we found when we did perturbation theory up here. That gives you this extra term, exactly. Okay, so that's just checking that we're not making any mistakes. Okay, and so in reality, in this problem, apply a constant force to the harmonic oscillator. Perturbation theory converges very nicely. In fact, second order in perturbation theory is already the exact answer for the energy, and it's doing nicely for the state as well. For homework, there's a new homework set out today, and for homework, you're going to be treating a case in the harmonic oscillator where perturbation theory sometimes converges and sometimes does not. And by working the problem, you'll get to see when it converges and when it doesn't. Okay, questions on that example? Okay, so we don't want to just do examples where we already know the answer like this one, because that's not what perturbation theory is good for. It's good for cases where either the problem is too hard or impossible to solve without perturbation theory. So our next example, which we won't have time to do today or finish today, but let me say what it is a particle in a one-dimensional box with a small bump. So there's lots of versions of this problem that are popular for PhD candidacy exams. Here, the potential is going to look like the following. There's x. This is the potential V of x. This is going to be a box of side L. So I'm putting L over 2 and minus L over 2. If you're outside there, then the potential is infinity. Okay, and that's the particle in a box that we already solved last semester. But now we're going to add to this a little bump, and to make things nicer, I'm going to make the bump be symmetrical around the origin. And so this is from minus A over 2 to A over 2. And this is going to be V0. Okay, and so in this example, perturbation theory is, again, pretty much always going to converge. And the reason for that is because this little bump that I've put in is always small compared to infinity, which is what's really setting the energy scale of the rest of this. Okay, and so next time what we will do, we're about out of time for today, is we're going to find the energy and wave function of the ground state. We're only going to do the ground state in class, and for homework, you get to do the first excited state, which should be similar, or is similar. Okay, so you'll want to pay attention to that, because when you do the homework, it will be changing a few things, but the general strategy and things like that is pretty much the same. All right, that's it for today. You owe me homework today. I forget when I said homework is due. Did I say homework's due at midnight, or did I say homework's due at 5 p.m.? In any case, whenever it's due, it's due. It can be due at midnight today. I don't care. But as usual, as most of you know, you should be turning in your homework as a single PDF file. Pretty much the way you turned it in last semester is fine with me. And so send those by email by the end of today. All right, go ahead.
Yes, this new homework that you posted, is that due next Wednesday?
That's due next Wednesday, yes.
Would it be possible for you to postpone the new homework due date to next Friday instead?
Is that good for some reason? Is Friday a better day? I thought I heard last semester that Friday was not a good day.
But the reason is 'cause there's another homework due on Monday for another class. That's why I'm asking. If everyone else is okay with it.
Okay, well, Monday, I mean, there's only so many days in the week that we can move things around to. Did you have a comment, Cassie?
Yeah, I know that when some of us don't like Wednesday.
Some of us don't like Wednesday.
Or sorry, don't like Friday.
Don't like Friday.
Yeah, don't like Friday.
All
I'd
right.
be okay pushing it back till Thursday, but
Yeah, I mean, I guess there's no reason we have to have homeworks due on a day where class is, since we're not meeting in person anyway. So why don't we compromise and make it Thursdays? Is that good?
Thank you.
also
All right.
I don't see on your homeworks a certain time that it's due or in the syllabus. But I know last semester we always had midnight, so.
Yes.
Yeah, I don't actually remember. Let me see what I put on the syllabus. Here, let me stop the recording here.